All right, good morning, everyone. It's Monday, May 11th, B period statistics, last day of class for the seniors. And welcome. Hopefully it'll be a productive class. A couple housekeeping chores. Mr. Tomlin, Mr. Walden, I never received your Chapter 6 tests for unknown reasons. So if you can get them to me, better late than never. Any questions, comments, or concerns reference that? They were due a week ago, last Friday, about 10, 12 days ago. Mr. Hellman, if you said something, you got to unmute.
So I didn't know we had a test there.
Pardon?
I didn't know we had a test.
Yeah, it was, let me go back and look at my notes. Go back to April 29th. We did a review that day and put the test online that day.
Okay, I'll take it.
It should be all, it's available on Blackboard on April 29th. There's a Dropbox there for it. If you want to review, of course, you can go to the YouTube website and rewatch that class. Let's see. Yeah, you were absent that day, that's why. All right. Any other questions, comments? Any parting remarks from seniors? Guys that aren't seniors, we will we'll continue plugging. All right. For the next, we'll have 3 more classes: Wednesday today, this week, and then Monday, Wednesday last week. All right. Ideally, I'm supposed to kick you guys off, but you guys are supposed to have your cameras on for Zoom security procedures. All right. So I can see your smiling faces. All right, so here's the plan of the attack. We worked on section 7.1 last Monday and Wednesday. I did an exercise. I ran over the PowerPoint slides, but I really kind of emphasized the exercise because that really was an application of 7.1. And I think it's more meaningful and productive than just going over a set of PowerPoint slides. And then there was a exercise I loaded up on Wednesday that you guys are supposed to drop in Blackboard on Friday. Looks like only 2 of you did it. So I'm going to go ahead and post it now and talk about it, because then we're going to jump into 7-2, which is kind of a very, very, very similar to 7.1. So we're going to move through it fairly briskly, and then we're going to create a sample. If you haven't already kind of ingrained it in your system, we're going to create a SDSM, sample distribution of sample means, which we did in section 7.1, but we also did a sample distribution of ranges too. But we're going to work on means, and the exercise is going to be very similar to what we're going to do in the PowerPoint slides, except our population is going to be a slight derivation of the numbers that the PowerPoint slides in the textbook use for 7.2. So you'll have those 2 as references. As soon as class is over, I'll load that stuff up on Blackboard. So by 11:30, I'll have it on, if not sooner. All right, we ready to go? Questions, comments? I'm excited. Seniors excited? All right, so here we go. Let's see, what do I want? All right, so this will show up. Yep. Move things out of the way here. Let's see. Let me blow this up just a little bit for you guys, so it's maybe a little easier to read. All right, that's better. Okay, so this was the exercise from 7.1 and forming a sample distribution. And I'm just going to kind of go over what I was looking for. I created a couple that were submitted, so just check your work versus what discuss here. It says manufacturers use random samples to test whether or not their products meet specification. These samples could be people, manufactured parts, or even samples during the manufacturing of potato chips. Subway sandwiches, Wendy's hamburgers, Jimmy John's, wash machines and dryers, Corvette Stingrays, any of those things. Do you think all random samples taken from the same population will lead to the same results, and why or why not? No, because if they always led to the exact same results, then we wouldn't be doing these sample distributions of sample means. This is particularly applicable for chain outfits, just like the fast food restaurants I just mentioned. They want that Jimmy John's sub to taste the same in Richmond, Virginia, as it would in Seattle, Washington.
Sir, did you send this to our email, or is it in Blackbot?
This problem set I put on Blackbot after, either sometime on Wednesday, either before or after the class. I can't recall which one. Okay.
Can we still turn it in for partial, or?
Yes, sir.
All right.
But they do this random sampling to see if there is variability, and of course, ideally, they want to minimize variability, just like candy bars, Hershey Kisses, anything that's in mass production. You know, these large major companies want to have, you know, whether you buy it at Wawa or Kroger's or whatever, they want each one to be identical to the last one because you're buying it because you like it and appreciate the taste. So they want to minimize variability. We talked about this back, I think, in chapter 2, where variability, you may not be able to detect it. A lot is very dependent on what the measuring instruments are for detecting variability. If they're very, very, very precise, you may be able to detect very minor, subtle differences in variability. If your measuring techniques and devices are not very precise or very get down to the hundreds or thousands or tens of thousands, you may not be able to detect that variability. Any thoughts, questions, comments on number 1? All right, number 2 says, what characteristic or property of random samples is typically sought, analyzed, or investigated during the sampling process? And we just talked about that. Variability, all right? Anything that's mass produced, they want to minimize the variability. I've used this example before. You know, you want the breaking strength of rivets used to assemble aircraft. They want them to meet a minimum standard, and of course they can't test every rivet because then there'd be no rivets to construct the aircraft. Again, you want very minute, if none at all, variability from sample to sample to sample. All right. Questions or comments on number 2? Number 3, it says, using the third table you created on the previous handout. And the previous handout they're talking about was that exercise that we did on Monday and Wednesday in class. Explain why the 25 different samples are equally likely and why the probability of 0 equals 0.04, probability of 1 equals 0.08, and so forth. And the answer to that was those are all theoretical probabilities. This isn't theory, and we've talked about theoretical probability versus experimental or empirical, which is synonymous terms, probability. All right. This is in theory, just based on the math and the numbers, what should occur. And we've talked about this before. Typically, empirical or experimental probability, so if we did this as a repeated number of trials or tests, the experimental slant empirical should trend towards the will trend towards the theoretical. Let me see what else. Yeah, all 25 outcomes are equally likely to occur. So each individual outcome had a probability of 0.04. All right, questions on that? All right, number 4 says, what is a sampling distribution of sample means? Sometimes your book, or you may see in questions, we'll say SDSM, and that's just an abbreviation for sampling distribution of sample means. We started doing frequency distributions back in chapter 3, I believe it was. And remember, and this is almost identical to a frequency distribution, meaning that when we get multiple samples, a distribution is kind of like, how do things fall out? Where do the numbers fall out? So I can organize them. Are there trends going on there? All right. Where's the data grouping or gathering? Where is it dispersed or spread out? And instead of being a frequency distribution, how often something occurs, it's a sampling distribution of sample means. So we're taking multiple samples of a specific sample size. We're going to talk about that more today, today's slides, of maybe 5 samples, 10 samples, 15 samples, or sample size, or 20 sample size. And then we take the means of each one of those samples and we analyze the means. So we're kind of getting more precise, kind of deeper into the weeds with that. So the distribution formed by the mean, all possible samples, okay, all possible samples of a fixed size taken from the population. And don't always think of a population meaning people. It could be wash machines or flat screen TVs or sub sandwiches. All right. Comments, questions on number 4? All right, last question is: a sample of size 3 is taken from a population and a sample mean is found. Describe how this sample mean is related to the sampling distribution of sample means. All right. What I was looking for there is the mean of all your samples should be the mean of should be the mean of the sample population. Again, being that if you've taken a nice, random, representative, unbiased sample, it should be very, 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 very reflective of the population, just as if we were able and capable of sampling the entire population. Otherwise, our sample is anything we do with that sample is kind of going to be a moot point. It's not going to, how can we, if the sample's poor, how can we relate that back to the entire population? You're not going to have any credibility, and it's not going to be accurate. All right. Any questions on that guy? Anything not make sense that I can go into more detail on? Everybody good? All right. Let me come out of that. Let me change things up. There we go. All right. So this is section 7.2. This chapter is only 3 sections long. So you guys that are not seniors will get through this chapter by next week. All right. So actually this, and I'm kind of wonder why the book did this, because this section, this 7.2 is very, 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 very similar to 7.1. So if you kind of got the hang of what we talked about last week in 7.1, then this should be actually is an easier section, because one, you've got a little bit of foundation and background to rely on. And remember in 7.1, we did 2 sampling distributions, one of the means and then one of the ranges. So, this should be fairly easy and fairly fast. And if you just pay attention a little bit, the problem set with this, you're going to do the exact same thing with just a slight change of the population numbers. All right. Any questions before we get going? All right. Let's see if I can get these to move. All right. So some of this is going to be a little bit of review of last week, which is always good. And it says on the preceding page, we discussed the sampling distribution of 2 statistics, the means and the ranges. And that's what we did back in 7.1. We did the means and the ranges of that, what was it, 0, 2, 4, 6, 8, I believe it was, numbers. Many others could be discussed. However, the only sampling distribution of concern to us at this time is the means. right, so again, we're just gonna do the means this time, so we've actually cut our workload in half, which is always good. So let me clean up my scribble. All right. Sampling distribution of sample means. That's that SDSM I referred to just a little bit ago. All right. If all possible random samples, each of a size n. So now the n doesn't really refer, well, it doesn't refer to the number of samples. It refers to our sample size. Sample size. So that's a little confusing. I'm surprised statistics didn't use a different variable for that so that we don't get them mixed up. But for whatever reason, they didn't. All right. Each of a size n are taken from any population with a mean. There's our mean symbol, which you should have ingrained now. All right, and a standard deviation. There's our standard deviation symbol. Then the sampling distribution of sample means will have the following. All right. So what does this mean? Okay, what's that mean? It's saying the mean of all your samples. So if we take, like, let's just arbitrarily say we take 10 samples of a size of each sample size of 5, and we take the average of each one of those and an average of them collectively. The mean of the samples should be the exact same or very, 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 very close to the mean of the population. That's what that's saying. The reason it would be very, 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 very close is if we do some rounding. Right? It may not be exactly the same. So that's the mean. And then the standard deviation, all right, of the means of those samples is going to be this formula, all right? So it's going to be and we're going to actually change the name on it and call it something different. It's called standard error. It's actually the standard deviation of the population divided by the square root of the sample size. So anytime we're going to divide that by something, we know it's going to get smaller. And remember, standard deviation is a measurement of how dispersed or spread out the data is. So you know when we're dealing with many samples and we're dealing with the means, the data is going to start kind of bunching up together. And I'm going to show you visually what's actually occurring there, right? Anytime I divide a value by any number, it's going to be a smaller number, right? I guess unless it's a fraction or decimal, but in this case, it's always going to be a smaller number, meaning that the data is going to be kind of gathering around the mean or coming closer into the mean. We'll see this visually here in just a couple slides. Furthermore, if the sample population has a normal distribution, right, and the sampling distribution of the means will also be normal. So let's pick that apart for just a second. If the population is a standard normal curve, bell-shaped curve, which we love because we can do all those probability calculations, the sample and the sample means is going to be a standard normal curve. But more likely, it's going to be a little more grouped together. It's going to be more like this because, again, our standard deviation is going to get smaller because we're dividing it by the square root of our sample size. Don't worry about trying to memorize this because when I show it to you graphically, it'll I think, make more sense. All right, questions before I move on? All right. Okay, remember I told you, this is the standard deviation of all your sample means. And unlike not changing the symbol n, statistics now is going to change the name of it from standard deviation to standard error. I'm not going to get real hung up on that. It's still standard deviation, right? But just so that you know, if you read it in the literature or you see it next year when you're taking stats at college, it does ring a bell. All right. So the standard deviation of the sample means is called standard error. That's the takeaway. The standard deviation of of a bunch of sample means is called standard error. All right, central limit theorem. That's not the identifier for Charlotte Douglas Airport for you guys that fly a lot. All right, it's called the central limits theorem, or CLT. All right, so and what the central limit theorem is, it's kind of like a property. It says the sampling distribution of sample means will more closely resemble the normal distribution as the sample size increases. All right, again, don't get too hung up in the verbiage. What that is saying is what I already said, and when I show it to you graphically, I think it'll make sense. And it's not something you have to memorize. It's just it's a theorem or property that will occur. All right, which is why we're doing all this. Where we're taking multiple samples of the exact same size and dealing with the means. Is it makes everything be a standard normal curve, and just like we did with the binomial probabilities, and we wedge that into a standard normal curve. It then gives you the latitude to do all this probability calculations. So we keep trying to push everything, if it's not already there, towards a standard normal curve, because we can do all these probability calculations. And it says if the sample distribution is normal, then the sampling distribution of sample means is normal, as stated previously, and the central limit theorem is not needed. And again, once I show this graphically to you in a couple slides, it'll make more sense. All right, questions or comments before I move on? Get the slides to move for whatever reason. Yeah, let me clean up my mess. But, here's the but. If the sample population is not normal, meaning it's not a normal standard distribution or bell-shaped curve, the central limit theorem tells us that the sampling distribution will still be approximately normally distributed under the right conditions. We're going to talk about what the right conditions are. Meaning we're just going to increase the sample size, all right? And we've talked about this in previous sections. We've looked at some of similar graphs. If the sample population distribution is nearly normal, the X-bar distribution is approximately normal for a small sample size, all right? We don't have to do anything. Remember when we were doing that PQ and P times Q and the binomial, where we did P times N and Q times N, all right? What this is saying is if the population is normally distributed, we don't have to mess with this sample size. Remember when we did the PQ and the or P times N and Q times N, and both of those numbers had to be greater than or equal to 5. And if that P got further and further, probability of success got further and further away from 0.5, we had to keep making that N bigger and bigger. Very similar kind of scenario occurring there. Very similar scenario. So if you're familiar with that and that rings a bell and reminds you of stuff, it's almost the same type of scenario. It says when the sample population distribution lacks symmetry, N may have to be quite large, meaning up to 50. Typically, it's in the 20 to 30 range, and we'll see that graphically here in a moment, before the normal distribution provides a satisfactory approximation. All right. And I know this is kind of dry, and by combining the preceding information, we can describe the sampling distribution of X-bar, or of the means of the samples, in this way. The location of the center mean, all right, we're always familiar with that. Remember our standard curve, our mean was always right in the middle and at the apex of that curve, right? Always right in the middle. And, 50% of the data was to the left, 50% of the data was to the right. A measure of spread indicating how widely the distribution is dispersed is the standard error the mean? I don't care if you call it standard deviation, it's our standard deviation the mean. I'm not sure why change the name of it, but they do. An indication of how it is distributed. All right. Again, this is just kind of leading up to, we're going to take a look at these graphs here. And hopefully we'll tie all this stuff together. Let me see something here. Let me see something here. Yes. Yeah, I'm going to go ahead to the graphs and then I'm going to come back. All right. So what they're referring to is, let's just say, and we kind of did this last week with two of those graphs. If I have a population and I graph it, and each event is equally likely to occur, which is what this is saying here, right? And then I remember when we did this last week with that 0, 0, 0, 2, 0, 4, we created a sample size of 2. It started getting, the shape changed fairly dramatically. And we did this with those two graphs of the sample means and also the range. If I increase that sample size to 5, then I get a fairly standard normal curve, right? If I increase that sample size to 30, you can see all that data really coalesces around the mean, all right? So probably, a sample size of 5 to 10 is more than sufficient, all right? And this is that central limit theorem. If I keep increasing the sample size, I can get that thing to look like a standard normal curve, even if the population does not. And I'm just increasing the number of samples and I'm dealing with the means of all those samples. Does that make sense? All right, I'm going to give you a couple more examples, kind of a similar situation, again, just to kind of drive the point home. All right, let's see here. All right, so this thing doesn't even look anything. This is almost like an opposite standard normal curve. Here we got the dip in the middle and the high part on the other ends. So we increase the sample size to 2, and now we kind of got like not a bimodal, but almost a trimodal, where we got 3 different peaks here. All right. So sample size of 2 is not going to cut it. And then we get to a sample size of 5, and it is starting to look like a standard normal curve. All right. And you go to 30, and now you've got this thing where everything's right around and real close to the mean. So again, maybe a sample size of 10 to 15 or 10 to 20 would be more than sufficient. And this is that central limit theorem, that CLT, where we just keep increasing the size of each sample to get this thing to be a standard normal curve, which then gives us the opportunity to doing all the probability calculations like we've been doing for the last, probably 8 weeks. Let me see, I think there's one more. Let me see if I can get it to go. Yeah. All right, here's another one that the population doesn't look anything like a standard normal curve. And then we just take samples from that population, size of 2, still is kind of definitely coalescing well to the left, or kind of skewed to the left of the graph. 5 still skewed to the left. And then we get to 30, you can finally see that you got that standard bell-shaped curve. All right, again, that's CLT, or central limit theorem. All right, questions or comments or anything I can clear up on these graphs? I think that's the last one. Let me see. I think there's another one. Says all 3 non-normal populations, and that was this guy, and that guy. See, these are the 3 that we just looked at. The population is not normal in the first one. The population in the second one is not normal. Matter of fact, it's like, kind of like the inverse of a standard normal curve. And the population is on the third one was skewed well to the left. So all 3 non-normal population distributions seem to verify the central limit theorem. The sampling distribution of sample means appear to be approximately normal for all three when the sample size is increased to 30. All right, let's see here. All right, so let me go back. I skipped around. Any comments before I go back to before I jump to these graphs? Because I wanted to use the graphs to kind of drive home those first 7 or 8 slides. Anybody lost, confused? Okay, I think we stopped there. All right, so I'm going to walk through a couple things, and this is going to be very similar to the exercise that you're going to do. And if you could do it by tomorrow night so I can take a look at it before class on Wednesday to discuss with you, that would be outstanding. All right. So I'm going to kind of zoom through this because this is kind of a nice summary sheet. All right, the means of the samples and the means of the population should equal each other. All right, if not, they should be pretty darn close. The only reason it would change a little bit is if you did some rounding. All right, the standard deviation of the samples is the standard error is the standard deviation of the population divided by the square root of the sample size, which means that standard error number is going to go down dramatically, which makes sense, and that's why those graphs start kind of forming towards the center, and the data goes towards the mean. The distribution of sample means is normal when the parent population is normally distributed. If the population is normal, the sample mean distribution is going to be normal. If it's not, CLT is going to come to an effect because you can increase the size of your sample, is what number 3 is saying without reading it to you. All right, so some of that should be just kind of review and recap. All right, let's see if I can get this thing to go. Let me get rid of the scribble. The invert referred to is the size of each sample in the sampling distribution. See, that's where, and I'm not sure why statistics always likes to give different names to the exact same thing. And here we got 2 different things that we're using the same symbol for. It's not the number of samples, it's the sample, it's the size of each individual sample we're referring to now with the SAN. So I'm not sure why they did it that way. It's easily to get, can easily get confused just because of what you already know. All right, so this is, I'm going to kind of run through this fairly brisk pace, but this is what you're going to do for the exercise. Now it looks very similar to this. Instead of using 2, 4, 6, you're going to use 4, 6, 8 or 6, 8, 10. I forgot. One of those, you're going to use a slightly different number, okay? So I'm just going to walk you through. I'll post this set of slides on there, and this is actually right out of your textbook too. So if you have your textbook at home, it's section 7.2. You can use that as a reference and resource. So let's consider all possible samples of size 2, which is just like we did last week, that could be drawn from a population that contains the 3 numbers 2, 4, and 6. Let's look at the population itself and construct a histogram to picture its distribution. So 2, 4, and 6. Oops, darn it. Let me go back. All right. The probability of X equals 1/3, okay? Or 0.33, right? Because you got 3 possible outcomes, each one equally likely to occur. So it's 1/3 or 0.33. Doesn't look like a standard normal curve, right? All right, so here we go. And you're going to do the same thing on the worksheet. All right. So, why does it keep doing that? All right. So here's our 3 X values. It's either 2, 4, or 6. Each one is equally likely to occur. We should be almost pros that here's your frequency distribution, or similar to your frequency distribution. Now it's a sample distribution. What we've done, each one is equally likely to occur. The sum of all outcomes always equals 1. That's a check, all right? Now we're going to do, it just says multiply X times the probability X. And that equals this 3rd column. So 2 times 1/3 is 2/3, 4 times, and so on. All right? And all right. And if we add those all together and divide by 3, we get the value of 4. And this 3rd column is always the what? It's always the mean. It's always the mean. All right. Which, if we go back, I can't go back with drawing. All right. let's do the fourth column is this. This is where most people run into mistakes. It's this column squared times this column. You want to multiply the second and third column to get the fourth, but it's first squared. Let me see here. Yeah, actually, it's the first column squared times this. First column squared times this. So 2 squared is 4. 4 times 1/3 is 4/3. 4 squared is 16. All right, times 1 is still 16 is 16/3, right? And so we add all that up and we get 18.66. Okay. All right. And to calculate the standard deviation of this, it's that same formula which I've always given. You don't have to know it. It's this first column. Our question is fourth column minus the mean squared, and then take the square root of it. So our standard deviation of the population, we're dealing with the population, is 1.63. And our mean of the population is 4.0. We good so far? All right. All right. So now we're going to do let's list all the possible samples of size 2 that can be created. This is similar to what we did last week. So we got 2, 4, 6. So we've got 1, 2. We've got 9 different combinations of numbers here, right? And here's where this come from. Add the 2 samples together and divide by 2. Right? They're all averages, right? Nothing real confusing there. All right. Everybody good so far? I'm moving a little bit fast here. Make sure I get through this. I think we will. All right. So now, remember that first table we did 2 slides back was with the population. This is our sampling distribution of sample means. All right. So here's our means. All right. So we got a mean of 2, a mean of 3, a mean of 4, 5, and 6. All right. We had 1, 2. We had 2 3s. We had 3 4s, 2 5s, and 1 6 as a mean. All right. This column here is just the first times the second. All right. 3 times 1 is 1/9. 3 times 2 is 6/9, and so on. Last column is the first column squared times the second column. All right. This was a check I failed to mention. The sum of all possible outcomes should always equal 1, which it does. This third column is always the mean. And remember, the mean of our population in that previous table we did 2 slides back was 4.0, and this is 4.8. That always should occur. The means of your sample distribution should also be the mean of the population. Okay, here's the sum of x squared times the probability of x. All right, so if we do the same calculation, that fourth column minus the second or the third column squared, and we get a standard error of 1.15. And if you remember, the standard error before was 1.63, so it got smaller. It got smaller, right? All right. All right, so there's our graph. We went of that previous table we just created. Remember the previous one had three columns. It had 1 up here, we had the 4, and then we had the 6. Remember? So now we've got this. That was what the population looked like. Here's the sample distribution of sample means. You know, if we had more data, it'd be a more rounded bell-shaped curve, but you can see the appearance of it occurring or coming to the surface there, literally and figuratively. Okay. All right, so here's kind of a recap of what transpired. All right. So let's see if what actually happened is true to this central limit theorem and what should occur. It says, all right, so the mean of our sampling distribution is the same as the mean of our population. Sample distribution and the mean are both 4.0. All right, so that's a big check. Happened just like it's supposed to. All right, the standard error of the mean, all right, we came up with When we did it on the table, we came up with 1.15. Now, another way we could have obtained it was taken the standard error of the population and divided it by the square root of our sample sizes. And that also came up to 1.15. So that checked out. Right? So everything's kind of fallen in place just like the properties and theorems say they will. All right, let's see. The distribution became approximately normal, which it most definitely did. So there's another deal, another check mark that, yeah, it did what it's supposed to do. Okay. All right, so this is kind of a good kind of recap because I've already went over the slides that follow this next one. I think so. So let's just, this is kind of a good summary. The mean of the population and the mean of the sample distribution of sample mean should always equal each other or be really, really close if you have to do some rounding. All right. The mean of the standard deviation of the sample distribution of the sample means should equal the I don't know why they changed the values on us. We should equal the standard deviation of the population divided by the sample size, which in that case it was. It went from 1.63 for the population, and then we took divided that by the square root of the sample size, which was 2, and it was 1.15. So that number matched with that sample distribution table when we did the calculation there also. Okay, I'm going fast. I'm going to get through this. All right, so we did that, and that. Let me see if there's. All right, we talked about that. All right, last slide. All right, normal population sample and distribution sample means for all sample sizes appears to be normal. All right, it'll always, you can get it to become normal as you increase the N or the size of each individual sample. Right? Thus, you have seen an amazing phenomenon. No matter what the shape of a population, the sampling distribution of sample means either is normal or becomes approximately normal when N, size of each individual sample, becomes sufficiently large enough. You should notice one other point. The sample mean becomes less variable as the sample size increases, right? It becomes less variable because we divide the standard deviation by the square root of the sample size, which causes everything to kind of go towards the mean and kind of coalesce around the mean. Notice that as N increases from 2 to 30, all the distributions become narrower and taller. And that is the end of the story. All right. I know I kind of went through it fast, but again, this is really just kind of getting a little deeper into the weeds of almost the exact same thing we did last week. So I will, give me about 11:15, I will get the PowerPoint presentation loaded on Blackbaud, and I'll get the exercise loaded on Blackbaud. You're going to do, you're going to use, I think it's 4, 6, and 8 instead of 2, 4, and 6, and do the exact same thing. The tables there, you're just going to run the numbers and graph it. I've already set up the template for the graph. It's just a slight derivation of what PowerPoint slides we just did. So just use that, use the PowerPoint slides or section 7.2 in your text as a reference if you run into a roadblock or a snag, or you can come on my office hours from 2 to 2:30 each day this week, except Friday, we're 9 to 10. All right, questions, comments, confusion? All right, I know, again, today's the last day for seniors. All right, everybody, I've enjoyed having you in class. It's been a small class. Bad for you seniors just because of what's happened with how this last quarter has transpired, and a lot of the senior last quarter traditions have not been as they have in the past. It's unfortunate because you're only a senior once. But I know you're going to do well in your next venture. Hopefully we'll see you all on July 11th or 12th, the new date for graduation. We're supposed to have, we've got office hours on Wednesday from 2 to 2:30. I think they gave you some kind of instruction. If you got any problems, questions, concerns, check in then, or if you want to check in on class, pop in and be a surprise to the remaining 5 or 6 that are not, 4 or 5 that are not seniors. We'll go from there. And if any seniors want to make any parting remarks to their fellow seniors or anybody else in class, or to me, you're more than welcome to do so. We got a couple minutes left.
Love you, Mr. Gaffney.
All right. Thank you very much. Said,
Thanks, Mr. Gaffney, for putting up for me for 4 straight years.
You're welcome. You're welcome. Anybody else? Hopefully we'll see you on July, is it 11th or 12th? I've forgotten. One of those 2 dates.
11.
Yeah, seeing them, what? Actually, about 2 months, I guess.
Bye, Mr. Gaffney. Love you.
All right. Good luck and hope to see you at graduation. All right. Take care.